lab next week? Like, it's super long.
Yes. Yes.
Pre-lab is ridiculous. Yeah. It's really hard.
Yes. So yes. So pre-lab, report, extended, report. Extended to this Friday, this week.
I think it already is this Friday, but like, I guess having
The lab report, pre-lab.
I think it is this Friday.
Oh,
They have everything due Friday.
next week. Okay, so your GSI will let you know. GSI discussed this with me also. So next week, yeah. It does contain a little bit more material. Some of those we are about to discuss, so that will be useful extension. Okay, any other requests? All right, okay, so we're going to talk about kind of the essence of this course. That is the most fundamental, smallest building block of active circuit involving a transistor, and that is a single transistor circuit. Okay, so main topic today, single transistor circuit. Okay, and these are often used as a building block. So once we recognize their functions, it will help us. These are like alphabets, and we can use to read these circuits. So before we start, let's review what you learned in 16A, so one-port model. So if we have a circuit, and we can replace the circuit as either Thevenin equivalent circuit or Norton equivalent circuit. Thevenin equivalent circuit is represented by equivalent resistance and voltage source. Norton is represented by a shunting resistance and a current source. And you can transform a black box of circuit into either Thevenin or Norton. And I'm sure you have all done exercise how to do the conversion. This is very similar to how we will find input and output resistance. So we'll do some exercise in the lecture today. Okay, so amplifier, usually minimum configuration is a two-port circuit. So by a two-port circuit, so for example, this is a two-port circuit here. And again, these are kind of high-level abstraction. Inside this box, there could be one transistor plus biasing circuits, like what we will discuss today. It can be a more complex block of circuits, can have an op-amp inside or multiple op-amps inside. So this is basically a black box consisting of the LTI system, linear time invariant systems that could have gain in there. Okay. And interfacing to the two-port, we have the input port. Okay, two-port means here is the input port. Shown in this example as a voltage source and the series resistance here. And then there is an output port here. So these are the two ports. And for most of the circuits, for most of well-designed circuits, the circuit is usually unilateral. Unilateral means, well, the signal kind of propagates from the input to the output. And it normally has minimum backward propagation, okay? This kind of comes automatically from the transistor characteristics. This is not 100%. This is not something like a one-way mirror you only see in one direction. But the flow of signal from input to output is much, much bigger than from output back to input. So when we do the analysis, we basically will make this assumption. So these are unilateral circuits, okay? And the output port, so this output port here, it will depend linearly. So we'll be dealing with LTI system. So linearly on the current and voltage at the input, if you add something to the output ports, it could depend on the output as well. In one cases where the unilateral assumption is not valid, that means that there are sort of leak through from input to output. This is when there are overlap capacitances. We will talk about this in more detail later, but basically, think of you have a gate, and you have a source, you have a drain, and there are finite capacitance between gate and drain. So while you are feeding your input to the gate, thinking you are really changing VGS, okay, that signal also coupled through the drain, which often is the output through this coupling capacitance. So we'll talk about the impact of that when we describe in detail the frequency response of the biasing circuit. Okay. For now, most of the analysis, we're just going to assume the circuit is unilateral. Okay. So far, so good. So that two-port circuit, we can break it down to 4 different combinations. Voltage in, voltage out. In that case, it's simply a voltage amplifier. So it's a voltage in, and not shown here, but it's producing primarily output voltage here. Okay, and for this kind of voltage in, voltage out, voltage amplifier, the two-port circuit is represented basically by something inside this box here. So the equivalent circuit includes input resistance, R in here, a dependent voltage source with your voltage gain here. So AV is your voltage gain here. So this basically is your gain, voltage gain. And it depends on the input voltage, so it's linearly dependent on your input voltage. We all know transistors are nonlinear, so these are all small signal bias, and you oscillate around DC bias point. And RL represents whatever load you are driving it. So let's run through other combinations. You could have current in, current out. In this case, you have a current amplifier. Current, we usually represent the input part with a Norton equivalent circuit. Current is sort of more naturally to be represented by Norton equivalent circuit. Whereas voltage, we normally represented that by a Thevenin equivalent circuit. Okay. And here we have a dependent current source. So voltage source is denoted by plus minus sign here. Current source is denoted by the arrow. And the current gain, again, AI is the current gain, and I in is the input current coming into the two-port circuit. So it's not IS. Okay, there, as you see, if you attach the input port here, there will be a current divider. This is a current divider. Only the current that goes into the two-port circuit actually gets amplified. The shunting current does not. Okay, and again, typical load. So aside from these two, which is convert the same quantity to usually a larger quantity, we also have the cross type. So we have voltage in, but output we are mostly interested in current out, okay? So this is called transconductance amplifier, okay? Transconductance amplifier. So we mentioned the first half of op-amp is really a transconductance amplifier. So the input part looks very much like a voltage amplifier. The output part looks very much like the current amplifier. So if you compare here, current amplifier, it has kind of a Norton connection here. So here you have a Norton configuration here, and at the input, the source, you represented by a Thevenin equivalent circuit. Okay. You also have the other type, that's current in, but voltage out. Okay, and so the transfer characteristics is voltage divided by current, it's resistance, and it's output divided by input. So trans means output divided by input, trans resistance amplifier. So these are the 4 categories, kind of an exhaustive permutation. The reason we have all 4 of these, we have a need for all 4 of these. Sometimes we want to convert a signal which is really primarily current in nature, such as your lab 3, I think, you are flashing LEDs, you pick up your signal, which is current, photocurrent, and you want to convert that to voltage. So you would actually, what you have built is basically a trans resistance amplifier, sometimes also called trans impedance amplifier. This is also called trans impedance amplifier. Okay. The driver, the LED driver, is usually the opposite. You will have maybe a voltage source. You really want to drive LED, which is diode. You primarily modulate the diode current. So this will be the case. You will need a transconductance amplifier for your LED driver. So you indeed have a need for all different variety of amplifiers. These are generic model. So we haven't talked about what's inside here. And we can convert, even though a very, very complicated voltage amplifier, eventually into this 2-port model. The circuit we're going to talk about today are minimally complex, 1 transistor as an active element. So as you see in all these equivalent circuits, there are 3 important parameters. You look at all 4 of them. So let's see, there are input resistance, okay? There are output resistance, and there are gain. The gain depends on the particular type of amplifier. But every circuit has 3 parameters. R in and R out are kind of common to all of them. The gain depends on the particular type of amplifier. So these other 2 amplifiers also have R in, R out. Okay, they are placed in different position, either in serial combination or parallel combination, depends on the nature of the output stage. Okay, yeah?
When you mean that the gain depends on the type of amplifier, do you
Yeah.
mean like the units of the gain?
Yes, the units of the gain and how we calculate or measure the gain. Okay, so it is therefore important to be able to find the input impedance. Here, finding really means hand analysis. Be able to do small signal, KCL, KVL, and able to find this input resistance. This should be Z in, not Zing, okay? So the systematic way, or kind of a definition or a systematic way of finding input resistance is very similar to what you use to find the Thevenin equivalent resistance of a 1-port circuit. So here we will attach the load, because when the source sees the circuit, the effect of the load is also seen by the amplifier circuit. So we attach the load. So there are really 2 parts. We attach the load, and then we apply a test voltage source here, Vx, and calculate. If you're doing experiment, you'll be measuring this current. If you're doing analysis, you'll be doing KCL, KVL to calculate the current, Ix. And you should eliminate all the intermediate variables. Ultimately, they are only Vx and Ix. You take a ratio of the two that give you the input resistance. Okay, so input resistance, the two criteria are here. You remove the source resistance. So remove Rs. So we no longer have Rs here. The input resistance of the circuit should be independent of the source. When you eventually attach your input, that's when you connect your Rs over there. But ZL is seen by the source, so you will need to attach the output, RL or ZL. Okay. That's the input impedance. And the other important parameter is the output impedance. It's very similar, but we do need to include ZS now. So the two conditions, ZS attached, okay, it's the opposite of the two. So ZS attached and ZL removed. So output, we will take care of the output resistance separately. So these are removed. And also for calculating the output resistance, we will need to remove the input source. So input voltage, like Thevenin equivalent circuit, it will become a short circuit, okay? And if this is the input current source, these are small signal current source, and you replace that by open circuit. So exactly same procedure as you would do to find Thevenin equivalent resistance. And again, you attach a test source. Sometimes we write it as Vx. In some other cases, you see written as Vt. And in either case, we find Ix or It, depends on, these are just symbols, which symbol we use. Okay. So that's the general principle. We're going to practice this many times today. Questions so far? Yep.
ZS is the resistance of the source, right?
Resistance of the source. And the Z imply it's complex. Sometimes the source have capacitance. And capacitance, as you are experiencing now in your lab, they will impose a frequency limit. So to generalize that, the source resistance can become complex and become an impedance.
Is it by convention that we don't include the source for the input, but we do include it for the output, and we don't include the load for the output?
Well, it's not the convention, but I think it's physically logical if you think about it. What you're trying to find out is what does the source see into the two-port circuit. And if you have a load, the source will see the implication of that, right? And the RS is dependent. If I change a different source, I have a different RS. And this convention is important when we start to cascade multiple two-port circuits. Then this become important. Okay, so what are inside the black box? Inside the black box, simplest amplifier, single stage or single transistor amplifier. We have three general categories. A common source. So common source is shown here. You have a transistor, FET. Okay. Common. Here, common means which terminal is grounded. Okay. Why is ground referred to as common? You know, a two-port circuit. If you have a two-port circuit, right, it has a ground, and then the input is referring to ground as well, and output is also referred to ground. So whatever the grounded signal is common to the circuit, the input, and the output. So grounded terminal is referred to as common. So first type, source is grounded. There are 3 terminals in transistor. So, you can have 3 configurations. You ground the source. You can ground the gate. That's called common gate amplifier. Or you can ground the drain. That's called common drain amplifier. The one of them, we have already looked at them extensively. That is the common source amplifier. So we have looked at many examples previously already. Okay, and very quick overview. So you could, for example, draw the small signal circuit. These are also a very easy to analyze circuit. And this is the small signal equivalent circuit, R0. This is GM, VGS. And VGS here is basically equal to the input in this particular case. So input, you apply input here. So it's really between gate and source. Output goes out here. So here is V out. Okay. So here is the V out. The only difference here, we use a current source to bias it. Previously, we have seen examples. We use a resistor, RD, to bias it. So we can use RD as well, right? A current source is a better biasing scheme. So later we will have a lecture comparing different type of bias options. The lab you're doing now, you simply use a resistor to bias it. And later when we go to the biasing lecture, you will find that actually transistor is the best bias. And we also mentioned whenever you can use a transistor, it's actually better than a resistor. It is smaller, more compact, and usually give you better characteristics. So that would be this circuit, and it's so simple. We can finish all the analysis here. So the difference between RD and the ideal current source. Ideal current source, when we convert to small signal equivalent circuit, it is open or short circuit. A DC current source. Open. So that's easy. So this is the entire amplifier circuit. It's basically just the transistor itself. That's a whole amplifier circuit. And input equal to VGS. So output, VO, is basically equal to the current going up. It's plus minus. So it's equal to minus current, which is GM, VGS, which is V in, times RO. So your voltage gain, AV, is minus GM RO. Okay, so very easy. Two of the two fundamental parameters in a small signal equivalent circuit. Transconductance GM, output resistance RO, their product actually give you the amplifier gain in the common source configuration. We say we also care about input resistance. Input resistance are in. You are looking into the gate. You're looking in here, okay? So it's open circuit. Doesn't matter we attach RL or not attaching RL. So input circuit is infinity, okay? Output we would short the gate, so it's kind of all connected here, which makes VGS 0. So basically this term drops out, and you look in here, you attach a source here, all you see is the output resistance of the transistor. Okay, so R here is basically equal to R0. Okay, so this is kind of a trivial example of the two-port network. We are okay, just take straight to the small signal equivalent circuit of the transistor itself. It's really not that complex to analyze.
In the pre-lab 5, we are told to ignore the R0.
Yes.
I mean, if we ignore the R0, then the current direction going
Your lab, so your lab has, let's see, your lab, I believe, if I remember, you have RD, right? So if you have RD, and if you ignore R0, your small signal circuit looks like, so if you ignore R0, so no R0 here, but you have RD. So RD is equivalent AC ground. So you have RD here. So your equivalent circuit looks like that. And this is your V in. So your output is now, the current goes through RD. So your output is minus GM VGS times RD. So ignoring R0 just make your analysis a little bit easier, and rough order magnitude is still correct. If you don't, then R0 is here, okay? And instead of RD, this RD will be replaced by R0 in parallel with RD. Yeah?
So are we always considering R0 is a very good number?
Yes. So typically we will show more examples later. R0 it's useful to have some kind of order of magnitude in these typical transistors. Of course, this depends on the technology you use. This depends on the size of the transistor. So this is not a constant value. But if you are analyzing the circuit and wondering which term is big, which term is small, so you think they are roughly about 200 kilo ohm. So not quite a mega ohm, 200 kilo ohm. It's a pretty big resistor. And if you recall, when you design your bias circuit, your RD is on the order of a few kilo ohm, right? So this may be a few kilo ohm. 1 kilo ohm times 1 milliamp, that's 1 volt drop. So it's on the order of kilo ohm. So you see R0 is quite a bit larger than RD. In other words, even if you take the parallel circuit, they are still roughly equal to RD. Okay. All right. Let's go back to the amplifier here. All right. So common source, done. We have already talked about it. Okay. So next part, we're going to focus on the new configuration. Common gate, common drain. Common gate is kind of a little bit weird. Normally we think of gate as an input, but here gate is grounded. And where do we apply the input? We apply the input to the source. So this is where we apply the input. Where do we take the output? Here is the output. Okay, kind of a weird configuration. Common drain, okay, we again apply input here. Where do we take the output? We take the output from the source. So V out is here. Okay. And here we all show current source as a biasing circuit. And again, later we will show you this is actually indeed a better biasing scheme. Using it as a source rather than a resistor. This side is NMOS, okay, and PMOS is exactly the same, other than the source is connected to ground. Here, the source will be connected to the most positive voltage VDD here. So, in other words, the whole thing is flipped upside down. And likewise. Common gate, again, the gate is grounded, and the input will be fed into the source. Now is drawn on the upper side. Output goes out here, and similarly for the common drain. Okay, and the reason we need to have all three types, we need to have NMOS and PMOS version. It gives us a great flexibility. It's like your Lego blocks. You have many different shapes, and it helps you whatever shape structure you want to build. It gives you the flexibility to do that. Okay. Now let's let the fun begins. Okay. Common gate amplifier. So this is an example of a common gate amplifier, and we will have some kind of bias here, okay? And this bias can be set in a different way, or we can primarily set the bias by this current source here. If this is an independent current source, essentially when we attach IQ here, we already know VGS, right? So remember, these transistors all operate in the saturation regime. So the first thing you do is like what you're doing with your lab. You do DC analysis. You know the current source, so IQ here will be equal to 1/2 Kn, and for DC, VGS minus VTN square. So basically, you know VGS here. So setting the current is as good as setting the voltage source. Can you apply both? Well, you can, because the voltage here is floating. The voltage connected to the drain here is floating. So you can set both. You can connect independent voltage source here. You can connect independent current source here. Independent current source fix the voltage difference, VGS, between gate and source. And if you fix the gate voltage with this independent source, you kind of specify the DC voltage of at the source. Yes?
So you're designing your parameter VGS
Mm-hmm.
based on, so basically it's based on V bias? What parameters are you controlling to set VGS?
So if I'm doing a design problem, I would select, I basically will select IQ. So if this is a design problem, okay, I will select IQ because IQ, let me backtrack one more step. Later we'll find all the important parameters like voltage gain or current gain. These are all related to GM. So basically I select the GM I need. And GM is a function of I bias, IQ. So by selecting GM, I basically select IQ. So I select what's the DC current flowing through the transistor. I need this current in order to give me the required small signal gain. I cannot bias it any other way. Then the next step is to select my DC bias point. So select DC bias point. So here, I will select my VS, right? I will select what is my DC part of the VS. And this is fixed by VG, because VGS is already selected. By selecting IQ, I also select VGS. So these are all done. And I need to fix a voltage somewhere. So there are a lot of flexibility, but I usually want to choose, just like in your lab, I want to choose it in the middle of the variation. So I have maximum headroom and maximum legroom. So we've done all the DC analysis. We just assume we solve that. We know the GM. So now after we've done that, so we know the GM, okay? So we know the GM already. We know R0. These are the currently two small signal parameters we care about. And the next is to convert this into a small signal equivalent circuit. Before that, we need to know where is the input, where is the output. So this is your source. So this is your source. This is your input. You apply input to the source. So this is kind of weird, and we will explain why we will want to do that. And you take your output from the drain, okay? And if you have a load, you will connect your load here. So this is this part will be your two-port circuit. Is you exclude RL, exclude the source. That becomes your two-port model here, black box. Okay. All right. Okay, so we do it step by step. First, find the AC equivalent circuit. So the voltage source. So I ground the voltage source here. Okay, and I have earlier we have a current source bias here. Current source in the AC become open circuit, so we take that away, all right? And this part is the input, okay? And this part is the output, so we kind of keep it here. And VDD also become AC ground, right? So AC ground. So this become our AC equivalent circuit. We haven't substitute the transistor by AC equivalent circuit yet. So the next step is to replace the transistor. So the transistor is basically represented by this block here, right? So this is our transistor, standard pi model. By the way, the approach we are following here in the lecture deviates slightly from the textbook. Textbook introduced two different small signal models. There's a pi model, there's a T model. In the old days, people learned all different kinds. There are more than two, and pick the best model to use when matching to the type of amplifiers they are using. We felt it's a little bit cumbersome. You have to remember two models. You can actually derive exactly the same thing using one model. So we stick to the pi model, hybrid pi model. So if you read the textbook, you'll find the textbook actually used T model to analyze this. My suggestion is stick to the pi model. Just one model to remember. That's easier. Okay. So here is the pi model, and we have IS, we have all this. So next, we start to analyze the circuit. Okay. So what do we want to know? We want to know three parameters. Later we'll find this is actually a current buffer. So we will look at it from the point of view of current gain. So we will want to find current gain, AI. We'll want to find R in. We'll want to find R out. So what we do in the next few slides, we'll try to solve these three parameters. Okay. So far, so good? Okay. So here we can do a few simplification here to find the current gain. So how do we find current gain? Find current gain is kind of like a Norton equivalent circuit process. So the procedure to find current gain, so this is the two-port circuit, okay? And we replace the source with just a current source here, okay? So in this case, we have IS here, and this replace the real source. The real source actually, could be resistor in series with a current source, or it could be a voltage source, equivalent source with RS. So to find the current gain, we take out the RS. RS can be dealt with later, so we take it out first. And then we apply a short circuit. Okay, we apply a short circuit at the load, and then we find what is the output current that we generate in the circuit. So note that I draw the arrow of the output inside into the two-port circuit. This is the same as how we define it early in the two-port circuit. You can define it anyway, but this is matching to the two-port model that we have derived. So let's do that. So we take out the RS. So the RS is no longer here. We just have IS. And we provide a short circuit at the load. By attaching this short circuit here, RD, basically the effect of RD goes out. RD is in parallel to the short circuit. Everything will want to flow through the short circuit. Okay, so that simplifies the analysis a great deal. And we can trace the circuit here now. So we have ideal current source. So the IS goes here. It's an open circuit on the gate side. So the current will go only in this direction. It will flow either up or it will flow through RO. There are only two paths. Okay, and but we are not interested at this point where individual component. Both of them actually combine here again to a single current. They all flow through this path. So if we ignore the branch in the middle, this I out is actually equal to IS, but flowing in the opposite direction. So I out, without doing analysis, this is equal to minus IS. Okay, you can think of you're doing a KCL at generalize the KCL. You can say I draw a box. All the current go into the box have to be equal to all the current going out of the box. So that's the same definition as KCL. KCL says all the current flowing into a node